Hi, this is Sung, your online maths mentor, and I'm actually going to now launch into the first of the three types of mathematical induction type problems, and that is the sum or a series type problem, okay? And we in the last episode, we looked at the method, the three-step method, okay, of how to prove something by mathematical induction. SAP, show, assume, and prove. And we're going to use that same method in solving the first type of mathematical induction proof, okay? So let me go through each of these three steps as we apply it to this particular problem. So let me read it out, okay? It says, prove that 1 plus 2 plus 4 plus ... 2 to the power of n minus 1. So basically what we're doing is these are all powers of 2 that we're adding together in a series or in a sum type scenario, okay? So prove that that series is equal to 2 to the power of the next power of 2 minus 1 for all positive integers of n. So the key thing that we want to try and show is that it's true for all positive integers. It's true for n is equal to 1, n is equal to 2, n is equal to 3, 4, 5, 6, 7, all the way up to infinity, okay? Does that make sense? All right, so the first thing what we're going to do is we're going to show that it's true for n is equal to 1. So let's do that. So we always consider the equation above for n is equal to 1, okay? So on the left-hand side is equal to 2 to the power of 1 minus 1, yes? Which is equal to, what's it equal to? 2 to the power of 0, which is equal to 1. Does that make sense? All right, so basically what we're going to do, n is the first number, so there won't be any other terms before it, and then we just substitute 1 into n, right? So it's 2 to the power of 1 minus 1, which is 2 to the power of 0, which is just 1. Does that make sense? All right, on the right-hand side, what we've got is 2 to the power of 1 minus 1. Yes? So we're substituting n is equal to 1 into the right-hand side. N is equal to 1 on the right-hand side, which is equal to 2 minus 1, which is also equal to 1. Yes? So in other words, left-hand side is also equal to right-hand side. So n equals to 1 is true for the above equation. Does that make sense? Okay, cool. So we've shown that n is true for n is equal to 1, okay? Now what we do is step 2. Assume that n is true for some other number k, right? So what we do is assume n equals to k is also a solution to the above equation. Does that make sense? So 1 plus 2 plus 4 plus ... plus 2 to the power of k minus 1 must be equal to 2 to the power of k minus 1, okay? And this, we don't have to prove that it's true because we're just plucking some number out of the air called k, and we're calling it k, all right? So we're not trying to prove that it's true, we're just trying to assume that it's true. Right? Oftentimes people get hung up on this and they go, why are we doing that? And the answer to that is, it might not seem obvious why we're making n equal to k now, right? But if it's true for n is equal to k, and we can also show that it's true for the next number, n is equal to k plus 1, then if it's also true for 1, it'll be true for 2, because 2 is the next number after 1. And if it's also true for 2, then it'll also be true for 3, which is the next number after 2. And it'll also be true for 4, 5, 6, because they're all the next numbers after the number before. Which means that what is critical to this proof is after we assume that n is true for k, we've also got to prove that n is going to be true for the next number, k plus 1. So that's what we've got to do next. We've got to prove that n is equal to true for k plus 1. And then, just like a setup of dominoes, you know, all the dominoes just come crashing down. It'll be true for 1, 2, 3, 4, 5, 6, 7, all the way up into infinity. And yes, we have proved the question, all right? The premise behind the question that's being asked. Does that make sense? Okay, so let's do this. So assume, so now what we've got to do is we've got to consider n equals to k plus 1 as a possible solution to the above equation. Okay, so we've got to consider n is equal to k plus 1 as a possible solution. So we start with what we know to be true. So let me come around this way. So we're going to start with this. So 1 plus 2 plus 4 plus ... plus 2 to the power of k minus 1 equals to 2 to the power of k minus 1. Okay, that's what we know to be true. Okay, what we're going to do now is consider the next term in the series, right? So what's the next term in the series? What's the next number that we add? We're going to be adding the next number after this index, right? So the index or the power is k minus 1. What's the next number after k minus 1? The next number is just k, yes? So we're going to add 2 to the power of k to the left-hand side. And if we add 2 to the power of k to the left-hand side, what do we have to do to the right-hand side? Add 2 to the power of k. Does that make sense? All right, so that's what we're going to be doing, okay? And by doing this, right, if we can show that by adding 2 to the power of k to the left-hand side and the right-hand side makes the right-hand side equal to, yes, 2 to the power of k plus 1 minus 1, all right, then we've actually shown that this is true, for k plus 1 as well. Does that make sense? So what we've got to try and do is turn that into that. Okay? That is our goal. All right. So we know that that's true. All right. We're going to work with this now. Okay? So what we've got is 2 to the power of k plus 2 to the power of k minus 1. Okay? That is going to be equal to 2 lots of 2 to the power of k minus 1. Yes? And that's 2 to the power of 1 times 2 to the power of k, which is 2 to the power of k plus 1 minus 1. And see how that is equal to what we want? Because all of this added together gives you that, we've done the proof. We've done the proof. These 3 things added together are going to prove the premise that we ultimately want. Okay? And so the next line that we add in is our final conclusion. Okay? Therefore, 1 plus 2 plus 4 plus ... plus 2 to the power of n minus 1 is equal to 2 to the power of n minus 1 for all positive integers of n. Does that make sense? All right. And that is how we do a mathematical induction type problem.